Coming to the block diagram of operational amplifier, which consists of four different blocks. The first block is dual input balanced output differential amplifier. The second block is dual input unbalanced output differential amplifier. The third block is the level shifter stage, and the fourth block is complementary symmetry push-pull amplifier. Why the name we are going to call it as the operational amplifier means it does the mathematical operations like addition, subtraction, multiplication, division, logarithmic and anti-logarithmic amplifiers, as well as it also does the amplification purpose. So that's why the name we are going to call it as operational amplifier. The most of the amplification process is done by the first two stages, that is dual input balanced output differential amplifier and dual input unbalanced output differential amplifier. So what is differential amplifier? So this differential amplifier is constructed using the two common emitter amplifiers. They are connected in such a manner that the characteristics of those two transistors Q1 and Q2 will be same, and we are going to consider the resistances RC1 equals to RC2, RE1 equals to RE2, and we are making the power supplies plus VCC of both the common emitter amplifiers as the same, as well as we are making the VE as also equals to same. So we are connecting the particular two common emitter amplifiers in such a manner that since RE is common to both at both the emitters, we are taking the parallel combination of RE1 and RE2 and we are going to call it as RE. Since the emitters are coupled together, we are also calling this particular amplifier as emitter coupled amplifier. And the output is taken across both the collectors. The sinusoidal inputs are applied to the both bases of the transistors via the resistances RS1 and RS2, and we are considering this RS1 value as equals to RS2. When we are making V1 equals to V2, RS1 equals to RS2, RC1 equals to RC2, then the whole circuit, each half section is symmetrical to other half section, and the output voltage must be equals to 0. But practically, no two amplifiers are similar. No two transistors are being constructed in the similar manner. They are differed by certain values. So that's why even though we are making V1 equals to V2, the output voltage is not equals to 0 and it is proportional to the difference of the two input voltages V1 and V2. Hence, the name we are going to call it as the difference amplifier, where the output is proportional to the difference of two input voltages. Since the main building block of this particular operational amplifier is differential amplifier, the output of the op amp is also expressed as V0 is proportional to V1 minus V2. Coming to the different configurations of the differential amplifier, we can categorize into four different categories based upon how we are going to give the input and how we are going to take the output. If input is applied to the both bases, we are going to call it as dual input, and if it is only given at only one of the base, we are going to call it as single input. Similarly, if the output is collected across both the collectors, we are going to call it as balanced output. And if it is collected across only one of the collector, we are going to call it as unbalanced output. Based upon this categorization, we can classify the differential amplifiers into four different types. Dual input balanced output differential amplifier, dual input unbalanced output differential amplifier, single input balanced output differential amplifier, and single input unbalanced output differential amplifier. So the picture that we are going to see on the left extreme shows the dual input balanced output, since input is applied to both the bases and output is taken across both the collectors. Coming to the circuit on the right hand side, it is the dual input unbalanced because the input is applied to both the bases and output is taken across only one of the collector. Two more configurations on the left hand side. Since input is given to only one of the base and another base is grounded, it becomes the single input and output is taken across both the collectors. We are going to call it as a single input balanced out differential amplifier. Coming to the circuit on the right extreme, where the input is supplied to only one of the base and other base is grounded and output is taken across only one of the collector, this configuration becomes the single input unbalanced output differential amplifier. Coming to the analysis of the dual input balanced output differential amplifier. We can do the analysis as DC analysis and AC analysis. While performing the DC analysis, we are making all the AC sources as equals to 0. And while doing the AC analysis, we are making all the DC sources as equals to 0. So here we are going to take the dual input balanced output differential amplifier, and to perform the DC analysis, we are making the AC sources as equals to 0. So we are shorting the RS1 and RS2 resistances to ground potential, showing that V1 and V2 both are equals to 0. And when we are going to observe the circuit on the right extreme, which is designed for performing the DC analysis, here the circuit seems to be, each half section seems to be symmetrical to each other. So applying the KVL to the input loop, any of the input loop, we can calculate the current IE and we can approximate it to the collector current IC. So when we are going to apply the KVL to the emitter base loop of transistor Q1, it becomes RSIB plus VBE plus 2IERE equals to VEE. Since IB equals to IC by beta DC and IC is approximately equals to IE, we can write it as IB equals to IE by beta DC. We are rewriting the above expression in terms of IE, and we are going to get the value as IE equals to VEE minus VBE by 2RE plus RS by beta DC. Since RS by beta DC is much less than 2RE, we are neglecting this particular term, and IE is, which is approximately equals to IC, is given as VEE minus VBE by 2RE. For doing the DC analysis, we are going to calculate the operating point by calculating the present values ICQ and then VCQ. Similarly, we are going to get the present VCEQ value as equals to VCC plus VBE minus ICRC. And while performing the AC analysis, we are making all the DC sources as equals to 0. So that's why the resistances RC, which is connected to plus VCC, they are grounded. Similarly, we are not going to see any VEE source. RE resistance is directly connected to ground. And for doing the AC analysis, we are making the DC sources and applying the AC sources. So here we are applying the V1 and V2 as the sinusoidal signals that are applied to the two bases of the transistors. Here the transistor is replaced by its equivalent R model, where RE indicates the AC resistance of the transistor. So applying KVL to both the half sections, we are going to get the currents IE1 and IE2, and we are substituting the value of IE1 and IE2 in the expression of output voltage, and we are going to get the final output voltage V0 equals to RC by RE dash into V1 minus V2. Since V1 minus V2 is nothing but the difference of the two input voltages, voltage gain here value becomes V0 by VD equals to RC by RE dash.